Okay, I love this example because it brings together a lot of things. It involves a lot of the straightforward calculations you do when you deal with angular quantities. So we have moment of inertia 0.001 kilogram meter squared. It's a wheel, radius 12 centimeters, force of 0.05 newtons acting downward. We calculate the torque. Okay, well, the torque is a cross product of the r vector with the f vector, r vector being here, f vector being here, and that's equal to r perpendicular times f, where r perpendicular is a component of r perpendicular to f, which you can get by extending the line of f and projecting the radial vector, the r vector, from the axis to the point of application of the force, perpendicular. And then instead of doing a parallel projection, which would be like this, it's the perpendicular projection, which just runs along the perpendicular line. And that would be r perpendicular to multiply by f. Or you could do r times f perpendicular. Now, to do f perpendicular, I used a direction perpendicular to the r vector and just projected f straight onto that perpendicular line, okay? And here's my f perpendicular. So I could do f perpendicular times the r vector times the magnitude of the r vector, or the r perpendicular times the magnitude of the f vector. Now, the direction of the torque is the direction of r cross f, right-hand rule. R is in this direction. To turn r towards f, my hand has to be like this, not like this or this. And I turn my hand toward f and my thumb points into the board. So the direction of the torque is into the board. If we have an x, y, z coordinate system, with z being perpendicular to x and y, and also in the direction of the cross product of x and y, okay, as pictured here, then this cross product that's into the board is in the negative z direction, isn't it? So by the right-hand rule, r cross f is perpendicular and into the board, and it also in the negative z direction. Now we introduce the I, j, and k vectors, unit vector in the direction of the x-axis, unit vector in the direction of the y, and unit vector in the direction of the z. Okay? So then the vector into the board is going to be some multiple of k, because k is the vector that's in the z direction. Okay, well, let's see. What's the angular acceleration? Okay? Well, the angular acceleration, we divide the torque by the moment of inertia. Okay, that's just Newton's second law. You know, the angular version of Newton's second law is torque is moment of inertia times angular acceleration. Analogous to force equals mass times acceleration, where I takes the place of mass, tau, torque takes the place of force, and you get an angular acceleration as opposed to a translational acceleration. Well, we calculate the r perpendicular times f, and the calculation is straightforward. R perpendicular is just the projection of r onto the x-axis because of the direction of f being perpendicular to the x-axis. And other ways you could see it, but it's just going to be then the 12 centimeter magnitude of r multiplied by the cosine of 300 degrees by the circular model. Okay, if you want more explanation of that, look at the longer video. And that comes out to be 6 meters. So your torque is 6 meters times 0.05 newtons, which comes out, I believe, to 0.003 meter newtons. We say meter newtons instead of newton meters, so we don't confuse it with joules. The vector torque, because we want to use vectors, is then just this multiplied by a unit vector in the direction of the torque. And we just saw the direction of the torque is direction of r cross f into the board. That's the negative k direction, so we multiply this by negative k and we get this for our vector torque. So our vector acceleration is vector torque divided by moment of inertia. Well, there's your moment of inertia divided into this, you get 3 radians per second squared, and that's going to be times negative k. The change in omega then, in the next tenth of a second, if we assume that the torque doesn't change, which it does, I mean it changes by probably less than 20%, but maybe kind of close, might change by more than 20%, okay? Anyhow, we assume that the torque doesn't change, okay? So we're just going to get an approximation here. And we'll deal with changing torque, but you got to do integrals and stuff, so we want to save that until we really understand all of this. So we get the change in omega, the change in our angular velocity, is our acceleration, angular acceleration times our time interval. Well, there's our angular acceleration, this times negative k, time interval is 1/10 of a second, so we get this, 0.3 radians per second times negative k. Now, if initially our omega was plus 4 radians per second, meaning this thing's rotating in this direction about this fast, okay, what's going to happen in 1/10 of a second? Well, it's going to lose something like 0.3 radians per second in its velocity, and that's a little less than 10% of its velocity. But more specifically, well, our omega naught was 4 radians per second. We want to do this as a vector, okay? Well, 4 radians per second in the counterclockwise direction means we're rotating this way. By the right-hand rule, curl the fingers around this way, thumb comes out this way. That's the positive z direction, isn't it? So it's going to be 4 radians per second times plus k, not negative k, plus k. So when we add these vectors, we're adding a negative 0.3 radians per second times k to a plus 4 radians per second times k, and we're getting 3.7 radians per second times k. Now at this point, we could calculate our approximate or estimated change in kinetic energy very easily, and I'm not going to go through the calculation, but using this moment of inertia, that's your moment of inertia, and this omega naught and this omega f, we square them, take 1/2, multiply by I, and I believe we get negative 0.001 joule. Why do we get a negative? Well, we end up slower than we started at 3.7 radians per second as opposed to 4. So we're slowing down. Our kinetic energy is therefore decreasing. Okay? Now, let's calculate the delta theta for this 0.1 second interval. Okay, how far does the thing rotate? Okay, well, by all these assumptions, and this is, again, only an approximation, our delta theta is going to be our average omega times delta t. Well, if you can't do this in your head, if you reach for a calculator to average 3.7 and 4, you don't understand average very well, or you don't understand numbers very well, okay? And you probably haven't done enough mental arithmetic in your life. Now, some people aren't good at mental arithmetic. Some excellent engineers and mathematicians are bad at mental arithmetic. And if you just happen to be inherently not wired for it, okay, reach for your calculator, but that's rare that anybody with a decent mathematical aptitude can't do this calculation easily in their head if they simply go to the trouble. So anyhow, you get 0.385 radians per second for your average omega multiplied by delta, and that's times k, multiplied by the 0.1 second gives you this, which is about 20 degrees times k. So that angle's going to change by about 20 degrees. Then what? Well, next question is, what happens to the potential energy? Okay? Well, you got to go back to the definition of potential energy. The definition of potential energy is that it's equal and opposite to the work done by conservative forces. And I want to check time here, we're doing fine. Okay, equal and opposite to the work done by conservative forces, okay? And I'd commented in the longer video, if you only knew how bad it is to use MGH to calculate an electrostatic change in potential energy, you would save yourself the unbelievable embarrassment of doing that right now by putting this into your head and never forgetting it. This is probably the 8th time I've nagged you to do that, okay? Believe me, I know what I'm talking about. All second semester, there's very little MGH, okay? But there's a whole lot of potential energy. You have to know what it is. Anyhow, that's this. Well, that's going to be the conservative force, which is your 0.05 Newton gravitational force downward. That force is negative 0.05 newtons times your J vector multiplied by your change in Y coordinate. So what's your change in Y coordinate of the point of application of that force? Okay, well, the change in the Y coordinate is, well, from the Y coordinate here, which is the same as the Y coordinate everywhere across this horizontal line, in the Y coordinate here. So we see the difference in the Y coordinates. But the place we really want to see the difference is here on the Y-axis, because we can use our circular model. Y naught is just going to be the radius of the circle times the sine of this angle. Okay? This angle, in this case, would be 300 degrees. And this is going to be the 12 centimeters times the sine of the angle that you get when you add whatever this accurate angle is to the angle you started at. I'm guessing it's going to be around 320 degrees. So by the circular model, you easily get YF and Y naught, and then it's that times your J vector, and you get your delta Y, okay? And you multiply this all out, okay? Now, I commented the J vector dotted, this is a dot product, and I haven't told everybody what the dot product is, and there's some people in the class that don't know, most do. Simple enough. All I'm saying right now is if you take the dot product of the J vector with the J vector, you get 1. If you take the dot product of the J vector with the I or the K vector, you get 0. And same thing for any of these vectors. If you dot any of these vectors by itself, you get 1. If you dot it by any of the others, you get 0. Among these three, okay, K times either dotted with I or J is going to be 0, and so forth. You don't necessarily have to remember that, but take my word for it. The J's go away here for that reason. So you end up with this calculation, and that's equal and opposite to the change in kinetic energy by the Work-Energy Theorem, which says that the work done by the non-conservative force, by your non-conservative forces, is equal to the change in kinetic energy plus the change in potential energy. And there are reasons for that I hope you understand. But whether you understand it or not, this is an ideal case. Maybe it wasn't stated clearly, but that's kind of implicitly assumed. It's an ideal case, no dissipative forces, no friction, no non-conservative forces are acting, only gravity, and system's kind of coasting under the influence of gravity, so that delta KE plus delta PE adds up to 0, and delta KE and delta PE are equal and opposite. So when you calculate the delta PE, that's equal and opposite to delta KE, and what you get here should agree with what you get here.